Cool. So I'm David, and I want to talk to you about one of the weird through lines in technology that starts from some kids in MIT in the 80s through John Carmack in the 90s, all the way to kind of Fortnite in the 2020s, and how basically people's creative urge to make things with just about anything they have always succeeds, which is like my favorite thing in the world. There's actually loads and loads of code in here, so I'm sorry in advance. There'll be links to all the samples. Don't worry about it. Don't try copy type it in your notebooks or something. It'll be a bit weird. So we're going to get to building game engines later on, but the first thing we're going to do is we're going to start with a bit of a history lesson, because I want to talk about game modification pipelines. Video games, perfect. Cool. So in 1981, a couple of MIT students named Doug McRae and Kevin Curran started a company that they called General Computer, wonderful name for a company, and they released their first game. It was called Super Missile Attack. So what was interesting about Super Missile Attack was that it was an unofficial sequel to the arcade game Missile Command, which you've probably all heard of. And the two students that programmed it by building an arcade modification board that you could go into an arcade and physically solder onto the Missile Command arcade cabinet. They followed this up by making a game that was called Crazy Otto, using a similar technique to modify the Pac-Man arcade boards. And they accidentally invented what we now know as game modification by doing this. The mods took the existing game code and they added new features to the games to increase their difficulty, which was something that arcade owners at the time were really into, because there were like 5 games that existed and they were making loads and loads of money. So for their part, Atari did what Atari does, and they tried to sue them out of existence. Perfect. But actually, instead of succeeding in suing them, they ended up hiring them to make games. And as part of their settlement with Atari, they agreed to never sell unlicensed mods again. And Atari attempted to make game modification illegal as a thing to do, which is very on brand. So what actually happened is they sold the game Crazy Otto, the Pac-Man modification, to Midway, who owned Pac-Man, who released Crazy Otto as Mrs. Pac-Man. So there's a good chance if you've ever played Mrs. Pac-Man, you played the second ever game mod. I find this really fascinating because they were probably the first people to get into games the way that the majority of people get into games today, which is basically finding something, trying to tear it apart, and using other people's work as a game engine, as a basis for the thing. Now, in fact, this early trend of hacking arcade cabinets continued throughout the 80s and into the 90s, with some often really unpredictable results. So unless you were born in about 1980, you've probably, in fact, hands up if you've ever played Super Street Fighter II Rainbow Edition. Rainbow Edition, 1 person, 2 people. Right, perfect. So it was a hack so popular that Capcom themselves ripped it off. And they cloned it, and they finally released it on the SNES and Mega Drive as Street Fighter II Champion Edition, Championship Edition, which is a fan favorite version of Street Fighter II, because they bet the hackers sped up the game and made it more fun. So they ended up ripping off the rip-off. And the reason this was all kind of happening at this point in time was that early gaming was really self-contained. So each game you made required kind of mastery of the target platform, its hardware, the gameplay logic, and rendering code was all intertwined, right? And you can see at the time that early game ports weren't really ports at all in the traditional sense, but they were more kind of complete re-implementations of games by different people on different platforms. So they'd go and find, a company would find an expert to basically clone their games if they wanted to release it on the Atari and the Amiga and the Game Boy and the SNES. And because of this, what you would find is all these early ports of games very infrequently shared code. Like the code bases were fresh, really. So as games got more complex and bigger business, organizations kind of motivated by getting to market quicker started building games on top of their previously completed work. Now, this was most common with game series. So there are some weird anomalies in here, though, like Super Mario Brothers on the original NES was built off Excitebike because the locomotion of the bike moving is the same as the wonderful Mario running physics. So they literally cloned the Excitebike code and built Mario on top of it. As the 80s progressed, then lots of companies started to build internal game development toolkits and shared code bases, because they had the same problems that we all do today of trying to find that correct balance between reuse and re-implementation. So this led eventually through the late 80s and the early 90s to a boom in what was called at the time game creation kits, some of which were private. So famously, LucasArts had their Scum engine that Monkey Island and a bunch of other point-and-click adventure games were made on. Scum, of course, stands for the script creation utility for Manic Mansion. Other creation kits actually were launched as commercial products. So when I was a kid in the early 90s, I remember using Click and Play. I don't know if anyone else used Click and Play, but like it was really cool at the time. But famously, there was a guy called Gary who released Gary's Kitchens Game Maker. And it was probably the first. And it led to things like RPG Maker, which is a tool that's still celebrating its like 32nd anniversary this year. You know, RPG Maker still is where a lot of indie RPGs come from that get ported to everything. So while game engines as a language didn't quite exist yet as a term, everyone was kind of trying to work out how to generalize and share the code that made these games fun. Now, obviously, everything changed when id Software released Doom. This, whilst, of course, is not the first game that has ever been modded, you know, the truth is I feel like about 3 of my talks are just about how Doom is great and kind of changed everything. But it really did, you know. And in 1993, Doom popularized user-created game mods for the first time, kind of spurred on by the fact that they'd innovated on network multiplayer. So that led to a bunch of commercial licensing of the Doom code base, so notably Raven Software built Heretic and Hexen on it, which were produced by John Romero, who worked on Doom. And Raven took the Doom code base and they modified it and they changed the levels and they released it. When id then were following up Doom with Quake, Quake kind of introduced more than just level editors as a way to modify the game. So they pioneered kind of a C-like language that they called Quake C, like a C dialect, for making mods that were more involved than just making new maps or new textures. So Quake C was deliberately built as an extensibility point, compiled language based on C, designed by id, was kind of the pitch. And at that point, they realized they had something, right? And id started licensing the Quake engine to other game companies. So notably, Valve Software licensed the Quake engine. And actually, interestingly, if you ever wonder why, if you're familiar with Valve's games and the Source engine, the reason the Source engine is called the Source engine is id gave them the Quake engine on a gold CD in a folder called Source. And it was originally the gold Source engine, which eventually got renamed to the Source engine of today. And then finally, of course, Epic Games released the Unreal Engine, which is kind of the second watershed era because there's a fork in the road there. Followed by, and they were basically inspired by id's licensing model with the Quake engine, and they realized that they could make a business out of it, which I believe is doing pretty well for them if you check today. So this is mostly kind of lost to history, but also at the same time, famously, Duke Nukem 3D was built on an engine called Build by Ken Silverman. And whilst it's not really clear where the phrase game engine came from as a concept, it was probably id adopting the term engine from Ken Silverman, who called the Build engine, and then Epic kind of followed that language. So game engines as a concept were kind of lost and kind of retroactively labeled and attributed to this kind of mid-90s thing. So, and you know, the truth is when you talk about game design, especially in the 80s and 90s, so much of the terminology that we have to describe these legacy engines was really retrofitted onto them during the explosion of reusable engines through the late 90s and early 2000s, that then id started renaming their legacy technology. So you now have the id engines labeled as id Tech 1 through to, I think, 7 or 8 is probably Doom: The Dark Ages that came out last week. And obviously the Unreal Engine has version number histories that goes back consistently to this same lineage. So when we talk about game engines, especially to people that have never really built a game before, sometimes it's a little bit confusing to understand what a game engine really is. And I always like to use the analogy that a game engine is just like the web framework to business people, right? It's they're frameworks that provide a programming model for you to build games, and they tend to come with lots of optional libraries and modules that are capable of like really diverse ranges of things, right? So they tend to have like a really opinionated model of how they think a game should be constructed. So a game engine will normally come with modules like things for graphics rendering, handling input, audio, game logic and user code, AI systems, data streaming, networking, and a core frameworky components. And engines obviously are often modular and will often be customized by studios and extended by developers to make the unique parts of their games work. So, and then on top of all of that, engines are often useful because as long as the engine code itself can be ported across multiple platforms, you get to target a diverse range of hardware and games consoles today. So for reasons that we're going to get into later, I ended up building a game engine that runs in web browsers over a period of about 10 days, about 12 months ago. And I want to dig into the kind of subsystems that game engines are made up with some examples so you can see how it all really hangs together. Now, before I start, there's a really obligatory caveat here. There are many valid designs for game engines. These are just some representative examples of things rather than like an exhaustive deep dive into any one of these topics, because each of these things you could probably read entire textbooks on. So consider this like an introduction to the concepts rather than coming and correcting me because I missed one of your favorite techniques. I say that as a bit of a side eye to like the YouTube comments section when this eventually gets put on YouTube. Right. So we're going to start off with the most core concept of any, the game loop, right? And while not all games run on a game loop, most real-time games run on a game loop or something similar to it, right? So a game loop runs at a fixed tick rate and coordinates the execution of all of the other subsystems in the game engine. They poll for user input, they increment AI, they execute any user-defined kind of gameplay behavior or code to move the game forward. And traditionally, a game loop would run at a fixed refresh rate. So over time, a lot of engines have then divided that internal tick of the game logic with the update and rendering engine for better performance. It's this kind of fixed tick rate is the reason why if you try and play like DOS games on modern computers, they run at like 100 miles an hour and you can't do anything. And it's because they were locked to the refresh rate of machines at the time. And if you've got like a 240 hertz monitor versus like an old 60 hertz-ish CRT, you're going to break a lot of things. Renderers are probably the thing that people are most familiar with in game engines, right? So renderers or rendering engines, what they do is they take the game state as a bag and they generate the visuals of a game. Now, 2D renderers are generally concerned with render order and sprite animations and camera positioning and maybe some post-processing effects where they're used. While 3D renderers will deal with things like 3D asset loading, texture mapping, usually scheduling calls to be invoked on a GPU using a low-level GPU API. Now, generally, a 3D renderer will target multi-platform rendering APIs like DirectX or Vulkan or whatever the rendering engine of choice is, again, to help that kind of game porting thing. And it's really interesting because when you see people complain about game engines on the internet, mostly they're just saying graphics don't look good. And it's like that's one tiny subsystem of the whole thing. And then finally, we often have this concept of scenes. Now, not all game engines, again, operate over the concept of scenes, but a scene at a high level is an abstraction over the kind of thing that a game does at the time. So a game may have like a main menu scene and an options scene and a gameplay mode scene, and it's generally just ways to organize and collect code together. So you can kind of think about a scene as a logical grouping of game behaviors that contain game objects and NPCs and game world elements. And if you kind of zoom out to like an architectural pattern lens, what they really are is an organizational pattern for game assets and behavior. So to bring some of these concepts to life, I want to take a look at an admittedly slightly over-designed implementation of Conway's Game of Life, because you can write this in like 5 lines of code if you try hard enough. So if you haven't heard of it, the Game of Life is often sometimes just called Life, is a cellular automation game devised by British mathematician Jason Horton Conway in 1970. Now, the funny thing about Game of Life is it's designed as a single-player game where the initial state drives the entire behavior of the game, and then the game just ticks forward applying game rules. The game takes place in a 2D grid where each grid location can either be alive or dead, and each time the game updates, cells can change state. So the way Game of Life works is that any living cell with fewer or 2 living neighbors dies by underpopulation. any live cell with 2 or 3 live neighbors lives on to reproduce again, and any live cell with more than 3 neighbors dies as if overpopulated. And then any dead cell with exactly 3 live neighbors comes to life. So you end up with this like beautiful fractal-esque evolving thing. So what we're going to do is, knowing what we know about game engines now, we're going to build the most over-designed version of Conway's Game of Life. So this is just in JavaScript. It runs in the browser. Don't take it too seriously. We're going to define the most like minimal possible engine with a few interfaces that you might see here. So our game engine contains an instance of what I've just called an iRenderer and an iScene. Kind of written my JavaScript like it's C# to please everybody. So the scene can be set from the calling code, and then we've implemented our game loop. Now the game loop just calls update and render on our scene, and we attempt to step the world forward every 100 milliseconds using the browser's request animation frame API. So super simple, you load the page and it just starts ticking. We obviously need a little bit of startup code. So we've created a HTML file that contains a canvas for our UI, just a 2D canvas, along with some startup code that goes and finds the canvas. And then we create an instance of our canvas renderer and a game engine, and then we set the game of life scene and we start the game. So we hook the things up and we start it ticking forwards. And then our game of life scene implements this iScene interface. And in it, you can see that it has like an init, an update, and a render function, along with an iterator that lets us loop over each cell sequentially. That is what it does. And then if we zoom into our update function here, you see the game rules that I explained from the Game of Life. Now, don't worry about reading all the code in detail there. But all we're really doing is we're taking a snapshot of an entire grid, and then we're looping through each cell, and we're checking each one of those rules. We're producing a new grid, and then we are setting that as the current grid, ready for the renderer to render. And then finally, in our render call, we loop through our cells again, drawing a black cell or a teal cell, depending on whether the current state of the cell is meant to be alive or dead. So, you know, our iRenderer class, super, super dumb right now. All it can do is draw rectangles. I'm going to win a BAFTA. So the canvas renderer looks no different than this, right? It's super, super basic. All it does is takes the browser's native API to draw squares on a canvas and loops through. Now, the only interesting thing you'll notice here is that we are inverting our y-axis because, of course, game worlds tend to be 0, 0, bottom left, and browsers render top down. So we've got to flip the numbers a little bit. To be honest, if I hadn't told you that, you probably wouldn't notice it because it's really subtle until everything is upside down. Come on. Cool. And if we run this web app now, the Game of Life runs in our browser. We can obviously, I was expecting that to play. Do I have to click it? I click it. There we go. And yes, so if this will just run if we start it, and you can obviously write a Game of Life implementation much more succinctly than that without all that kind of over-design and architectural overhead. But I think it's a good example of some of these core concepts of some game engine primitives. Now, while watching the Game of Life play in its 0-player existence over and over is like the most fun that I personally can imagine having, most people probably want a little bit more from their games, right? So let's talk about input handling a little bit. So input handling subsystems are often used to convert input from gamepads, mice, and keyboards through what is often called like a key map or a button map. And the idea is that you define game actions and you have like an intermediate layer, which means that, again, you can adapt your game to touch surfaces and controllers and keyboards rather than just hard coding like when someone presses enter, something happens. So having this level of abstraction just gives you that little bit more portability. Great for accessibility as well, so all of the master esports players can rebind all your controls into something that's really bizarre. So we're going to need a game to rip off for our next example. And there was this excellent platform game that started out as a Flash game in 2010 called Thomas Was Alone, and it's playing out here. Now, it's a game about a computer mainframe gone wild with malfunctioning AI, and you should probably play it, not only because that sounds like a suspicious 2022 allegory, but 2025 allegory even, but most importantly, lots of its characters are just squares. And if most of its characters are just squares, I've got a great canvas renderer that can render all the squares in the world. So we're going to make our own version of this game. I'm going to call it David Was Alone. And we're going to start with the input handling. So building on top of our glorious Conway's Game of Life engine, we're going to add a new interface, an input device to our engine. And the input device implementations are going to be responsible for mapping inputs to an object containing the currently requested game actions. And thankfully, modern web browsers can deal with like just about any form of input by default. Gamepads, touch, and obviously keyboards. It's actually really impressive the amount of work that has been put into these APIs over like the last 5 or 6 years. They're really ugly APIs, but they do support everything. You can plug a PlayStation pad in through USB-C, just works. So we're going to update our engine to keep track of the connected input devices in an array. And then we're going to modify our game loop to pass this collection of input devices to our scene so that on each update, the scene can check what actions are being requested by the button presses. And then finally, we're going to expose a function for our startup code to connect them together, like a virtual plugging in of a control pad. And this is our keyboard wrapping class. We're just wrapping the keyboard event listener APIs in the browser and keeping track of what keys are pressed in a set, in a dictionary. So when the getCurrentActions function is called, we return an actions object with states that are set for left, right, and jump, the only things we can do in our little square moving game. And as you can see here, that using the Gamepad API isn't really much more complicated. It's just a bit uglier. There's a bunch of noise in it. And what it allows us to do is use the D-pad on any standard Xbox or PlayStation controller via USB. We're keeping track of which gamepad is connected and querying its button state in getCurrentActions here on line 26. I think this will probably work over Bluetooth as well. It doesn't actually have to be plugged in. And then finally, in our level scene, we can flatten all of our controller inputs down and move our hard-coded player character object so when a valid game action is requested, we shunt where we're drawing the square. So luckily, David Was Alone is entirely made up of squares, so our renderer is perfectly fit for purpose. Up in the top corner, you can see where we've changed the index page just to add our keyboard and controller inputs by calling this connect input devices function that we added on the engine. And look at that. Look at that. That's almost a game. Almost a game. David might be able to move, but he's also kind of defying gravity, which is not a wicked joke, and he's still very, very alone. So all we're doing here is just moving where the square gets drawn, right? It's not really truly a character. There's no behavior. There's no anything really yet. So at the moment, we don't really have any abstraction that represents a player character at all. We've just got a target square. And what we want to do is we want to introduce this notion of game entities. Now, game engines generally keep track of entities, and just like in any other kind of program, an entity is just a collection of data, sometimes stored alongside behaviors or functions. So building game entities for behavior helps us keep all of our logic out of the main scene class and organize our code base a little bit better. Similar to, I don't know, you're making like an MVC website, and you don't want to put all your logic in the controller. Game entities are the place to collect behaviors. And to add this concept of entities to our code base, first, all we're going to do is create a new draw function on our iRenderer interface. Again, we want to keep all that display logic abstracted away from the game logic. And then we're going to add a couple of new interfaces, so an iUpdatable interface that describes anything at all in the game world that can be ticked forward and updated. And then a game entity that has a physical location in the game world as some properties. So you see we've got X and Y coordinates, a width, a height, and obviously all those properties are then changeable. And you can kind of see where I'm going with this, right? So this lets us move all of our logic for updating the player into our new player character entity and generalizes out the level scene itself, which is now just responsible for calling update on every entity that's stored inside of the scene. So while it might feel like we're just kind of shunting code around here a bit, what this means is that we can now add different kinds of entities to our game scene, and they can all tick, and they can all have their own behavior, and they can all render. Now, this is only one approach to collecting behavior. So another common approach in game development is to kind of separate behaviors from the objects that they apply to. And there's often this pattern that is used called entity component systems. Now, the language is a little tricky here, so I want to talk about terminology a little bit. So in a traditional object-oriented design, data is co-located with functions that apply to it. So this is like classes, right? This is what classes mean. Now, games in the late 90s, pioneered by the game Thief, if anyone played it, came up with this idea of an ECS, an entity component system, which is kind of like the opposite of OO, where the data and the state of the system explicitly do not contain the behaviors, and there's a registration table of some kind that links data records and the things that apply to them. So various entity types get linked to their components, and then every time there's a tick, the systems operate on data rather than fetching a list of entities and running every single system inside of them. So mostly this was kind of a performance optimization trick at the time. But what this does is it changes our relationship from updating each object in memory to running the AI system that processes the logic over all of the entities that require AI to be applied to them. It's a little bit kind of like the visitor design pattern, if you ever use that. So inspired by this, though I'm not explicitly going to build an ECS here, in the 2D engines that I have built, I like the idea of including this idea of characteristics. The attributes that entities can maintain a subscription to that can be used on multiple entities inside of the game world. So for example, both the player and enemies can be physics objects where physics can apply to them, and gravity applies to them. I like using the word characteristics or behaviors because it avoids the often overloaded word component. Component is a terrible word that we use everywhere in all of programming, and it means about 100 different things. So I kind of don't like the way ECS uses component in the middle there. So to adapt our game engine, what we're going to do is we're going to add an update context that contains our game state, and that's going to be passed around on each update of the game loop. We've modified the game entity itself to contain an array of characteristics, and we made being updatable optional on the game entities themselves. So you can have really anemic game entities or ones that have stacks of characteristics. And of course, we've obviously added a very simple interface for characteristics to implement here, which just has an update function on it. Now, our level scene is now responsible for triggering the update function on any characteristics that our entities have applied to them. So again, we're dragging that level of abstraction a little bit further away from the scene. And optionally, also calling update on the entity itself if there's any logic present there. So what this does is it slims down our entity class to a minimum while allowing us to share characteristics between different entities. So one of the really nice things about generalizing these behaviors is that you can use one system to apply to multiple different categories of things, right? So ECS is kind of a form of composition rather than inheritance, much like you would see in other forms of programming. So you'll notice in this example that I've just added an instance of the characteristics to an array. Other engines, like real game engines, will tend to use like a registration table where they maintain single instances of these kinds of behaviors, and they look up the instance in the dictionary and then they apply it to a thing. But it's a toy example, so it doesn't really matter. So while moving our existing behavior into an ECS-like structure might make our code look a little neater, it's also prepared us to add physics to this toy engine, because having physics apply to something can be implemented as a characteristic that we can reuse. So physics simulations are really hard, and I'm bad at maths. So we're going to take that as the starting point here. Also, realistic physics are really, really deeply unfun. Like, there's a reason that Mario has like coyote time jumps, and when you run off the edges of platforms in video games, most of the time you didn't. Right? You can still jump when you're 5 pixels past the edge, because if you make a really precise game engine, people just die all the time and it's boring. So for our 2D side-scrolling platform game, we're just going to do Mario physics. Now, first what we need to do is we need to rework how we implement our controls. So rather than just forcefully moving our square a few pixels, what we're going to do is we're going to add some variables to store a current object x and y velocity. So rather than moving things, we're going to apply a velocity that will then be used by the physics characteristic. We're going to define a weight, and we'll use that to work out how fast things fall and also how things jump, and also a flag to work out if we are in fact jumping and not falling. So we've set these values in our player character class, and we're also going to add a physics object characteristic after the existing controllable one. So we collect controller input, and then we apply physics. We're going to update our controllable characteristic to increment or decrement our velocity when a button is pressed, but we also have a cap there so things don't zoom off the screen. And we're also going to add support for jumping by setting our velocity Y value when someone presses the jump button, and that's more of an instant kind of thing. So now we've got all that extra information in our classes, we can implement a physics object characteristic. Now, I'm not going to reproduce all of the logic of the characteristic here, but I want to call out a few important things in it. So firstly, we're going to calculate some collision points that line the bottom pixels and some midpoints of our bounding box around our character. Now this is important because it gives collision detection both a solid way to find the ground, you just check where the hot pop spots are on your pixels, but also there's a little bit of give so we can have that nice gentle collisions and jumps. So if you just have boxes around your characters and you're making like a platform game, what you don't want is when your character is falling, like the back leg to clip the back of an enemy and you get killed. Again, it's just really not very fun. It needs to be a bit more forgiving. So with those hotspots to do collision detection, we're going to apply gravity. So we implement jumping just by splitting the amount of time it should take for our object to fall by our 60 frames a second frame rate. And we slowly decrease the upwards velocity of our character until it reaches 0. And then we start decrementing again to give that nice Mario jumping arc. Actually implementing falling is done later when we calculate gravity, because gravity is just a permanent downward force. And all gravity really is a speed that the entity will fall if it isn't on the ground. So after adjusting our x and y velocities, we apply movement to the entity, shifting it to the next location on the screen. So a little bit of very, very simple physics. And this is what our game engine and scene files look like at this point. David can fall. He can now perish. He can reach his untimely demise, but he's definitely still alone. It's not very fun. Okay, segue, story time. Did you have Blue Peter in Norway? No? Brilliant. Cultural references, excellent. So in the UK, we have this kids' TV show called Blue Peter, and it's the longest running TV show in the world for kids. And they frequently show you how to build things out of like paper cups and toilet roll holders and glue. And one of the things that they do in Blue Peter is they show you like 3 shitty little cups, and then they say, here's one I made earlier, and they go away and they bring back like a sailboat and a ship and a spaceship and like 20 characters. So if you'll allow me to have a Blue Peter moment, I'm going to switch gears as we move to the next example. So a couple of years ago, I was making a game for a conference booth. It seems like they're very popular here today. There's games at like every conference booth on the floor. The idea is that attendees would walk by and they'd play a game, competing asynchronously with everybody else at the conference. So basically, I played Mario Kart and I wanted to rip off its like ghost mode, but I thought it'd be a fun thing to race like a platform game with asynchronous ghosts. I'd never seen that done before. Kind of like Super Meat Boy, if you've ever played that. So as we move on to talking about graphics, I want to introduce you to my magnum opus. This is the most complicated game I've ever made. It's called I Am Jam. A game where you, a humble orange, attempt to commit suicide and become jam. I Am Jam. So here's one we made earlier. Now, while I was working on the nuts and bolts of the game engine, someone else was working on the gorgeous pixel art to bring this to life. I did not do the artwork. It's brilliant. I'm not that talented. And other than how good they all look, there's nothing special about the graphics here, right? A couple of JPEGs with some background art, some keyframes for enemy mice that are trying to eat our intrepid orange as he tries to become jam, and some like cute clutter objects that you can scatter around the map. So what we need to do is we need to get these art assets into our game engine rather than just drawing squares everywhere. And that's why we need sprites. Now, Sprites, I'm sure you've all seen them before, are animation sheets made up of several images that get played like an animation. So they're basically digital flipbooks, right? So much like our earlier player character entity, in the codebase for IMJam, we had to design an entity that keeps track of the current animation frame so that as the game ticks forwards, we increment the current frame as the game plays out. So our game used two conventions. Firstly, we supported animated GIFs to make half of this problem go away. Perfect. Which we could write to our canvas directly. And it also supported a series of images in something called a sprite sheet. Now, sprite sheets are very famous in retro games because they were a very memory-efficient way to store lots of packed graphics data, where all the frames of a sprite are basically layered either horizontally or vertically, and all you're really doing is moving a pointer in memory as you're flipping through the pixels that you're drawing to the screen. So the character class in IMJam is a little bit busier than the one in David Was Alone, so don't worry about all the rest of the stuff in there. But we have two sprites associated with our character, one for them when they're alive, and optionally a sprite to draw when they die. So we have this really cute orange rotting animation if they get hit. It's kind of fun. So our character class here initializes its sprite on loading, and each time the game updates, it just calls tick on the sprite. And the sprite evaluates if it needs to flip to the next sprite. So if every time the game is ticking and you're ticking at 60 hertz, 60 times a second, your sprites will just flicker. So you need to like flip a sprite maybe every 10 ticks or thereabout. So our drawing logic is also like a little bit more complicated because the character state, whether they're standing or jumping or moving, can influence which sprite frame that we want to play. Because when we're jumping, we want to lock it to like a nice jumping animation. So once we work out if they're alive or dead and if they're moving or not, we call the draw function on the sprite, which renders it to the canvas. Now the sprite class itself is responsible for loading the frames of the sprite in each sequence. So we also do this clever trick where we have to flip the sprites. So we have some enemy classes here that are mice, and running left to right is great, but if you don't flip the sprites, they moonwalk backwards, which is very funny, but not really very realistic. So we're using a low-level image manipulation library called libgif in JavaScript to do this. And every 5 game updates, the frame counter proceeds forward, so the sprite class, when it's asked to draw, will automatically increment the active frame. And it works if I click it, I think. There we go. Behold, a tiny mouse trying to catch you. I love this. It's like my favorite. So the other interesting thing about 2D sprite-based games is that layers are used, much like in Photoshop, to render foreground and background objects to create like a sense of depth. So from back to front, it's kind of like using Photoshop. The background layer is the thing that's furthest away from the camera and usually contains static images that set the scene, like a sky or distant mountains. The middle ground tends to add elements that are closer to the viewer, and often includes things like trees or buildings or our clutter objects here. And then the foreground layer is generally reserved for the player character or the UI being closest to the camera. We actually have an even more foreground layer, so our orange can run behind some objects because we think it's kind of cute, makes it feel a bit more like it has depth. We're just using a Z-index system that we ripped off from CSS. So in our level map, we just apply a Z-index to different items so you can run between them. Kind of pretty cool. We've also, because we've got GIF support, we can use transparent GIFs for things like our little jug here, where a couple of the colors will blend as we move through. It's kind of nice. So for this game, we implemented like a super lo-fi camera, the final missing piece. And what it does is it works out what to draw based on the X and Y coordinates of the active player. Now, basically, all the camera really does is scroll all the background assets left to right. So really, your player character is running in the same place throughout the game. It also makes sure not to scroll off the edge, so it kind of caps and starts rendering the sprites further towards the edges as you get to the edge of the level. Super, super simple. That's the whole camera class. So traditional 2D games, when they're being built up like this are often made up of things called tile sets and level data, right? And again, this is another performance trick from older video games where you're in like a memory-constrained environment. So generally, your level data would refer to tiles that were loaded into memory and then painted across the screen. That's why games like Mario, etc., uses quite a limited set of sprites. And there's some really funny things like they reuse different assets with different colors painted over them for different things, and you don't really notice. The truth is, in a browser on modern hardware, all this data, 130 kilobytes. So we're not going to do any of that at all. We're going to use an incredible level format called JPEGs. Perfect. Not really breaking any performance budgets. Now, collision detection is a big mathsy thing that is different depending on 2D games and 3D games. What we've done in our 2D engine is we've implemented something called bounding box collision detection. Now, this is probably the most common thing that's used. You'll see it in Unity, you'll see it in Unreal Engine. And each of our entities basically has a box drawn around it with various collision points identified to do different checks of intersections. Now, the nice thing is this is really relatively inexpensive. So as the game ticks forward, the player character checks if it's colliding with the environment. And the enemy entities check if they're colliding with the player. And we make this really cheap by just checking the front nose, the back foot, the middle bit in the middle, and the top right. So you just, whichever way you're going gets checked for collision. So if you ever used any game engines like Unity, you might have heard these collision detection routines being called box colliders, or the wonderfully named AABB, which stands for Axis Aligned Bounded Boxes. And often that's used in 3D games, and it's called Axis Aligned because they're 3D objects rather than just 2D. So we use this really fun little hack as well for geometry collision detection, because I didn't want to write a whole geometry system at all. So what we do here is we just made a complete second image, exactly the size of the background, and I colored it in flat colors. So we've just basically got a collision map where black things are solid, red things kill you, and white things you can pass through. This is really easy to do in a browser because all we're really doing is loading an invisible JPEG, and then as we move through the scene, we check the pixel color at the exact same location that the player is currently at on this secondary image to see if they can move or not. If you had obviously drastically larger levels, this approach would probably not scale, or you want to do something a little bit different. But honestly, in current hardware, with the current scale of systems we have, this will work just fine for most 2D games. And the best bit is we got a free level editor, Microsoft Paint. Perfect. So the collision detection code in this version of the game just scans downwards to check for the color black to work out if the player is on the floor. Now, our enemy collision mostly works based on those same hotspots. The easiest way to understand collision is just to see it in action. So the Jam game contains this diagnostic view, which I was really proud of writing. I lost only an hour of my life to it, but you can kind of see the bits that we're checking for collisions and the bounding boxes and the underlying collision map. I think the good example here is if you look at the back of the enemy mouse, the long box, you can see that basically if the red bit clips through the back of the mouse, you'll never die. And that was like one of the best bits for game feel. So our code to deal with player death exists in the update function of the enemy entity. On update, it just checks if you are currently colliding with the player and if the player is alive. If those conditions are met, then the entity it collides with has this characteristic that we call killable. Sounds great, right? Very grim. Which in this game just means has a health bar, and 1 health point is the entire gameplay logic. So finally, I want to talk a little bit about the mouse AI. Not the same AI that everyone is talking about in every other talk. AI in games is like this huge, vast topic that covers multiple different approaches and programming styles that it'd really be impossible to make a dent in using examples here. The way it's triggered, however, is generally consistent, right? So it's just another game loop-driven system that updates every nth tick, and the AI for each entity, or the AI subsystem processing the game entities, executes some kind of logic and makes our player do something. Now, most games have some kind of pathfinding AI, is the most common, using either something called navigation meshes, where people basically paint their levels with invisible lines that AI can follow, or common algorithms like the A-star algorithm, which is a variant of Dijkstra's pathfinding, and then a series of other techniques on top. So famously in games like Halo popularized using something called behavioral trees, where characters have a set of actions that they can pick from, while there's another approach which is wonderfully acronymed as GOAP, goal-oriented action planning, which is quite popular in games with emergent gameplay, where game entities are given sets of goals that they have to meet in levels and criteria to evaluate whether they've met them or not, and a set of choices to make. That was popularized mostly by the game Fear. The games of the late 90s were particularly interesting, with loads of experiments in using things like neural networks. So if you ever remember the game Creatures, the little Tamagotchi-style things, they use neural networks. Black and White use neural networks. Finite state machines were used in Doom and Half-Life and continue to be quite popular with enemy AI. And then there's a bunch of hybrid AI approaches, like famously the game Left 4 Dead has both enemy AI and what they call the AI director. And all the AI director in Left 4 Dead does is watches to see if you're not doing anything, and if you're not doing anything, it tries to scare the shit out of you by throwing more zombies at you, and increasingly scarier zombies until you do something. But it's interesting because it's a good example of AI being used for something that isn't obviously visible in the gameplay. If you're interested in deep dives in these topics, there's a really great YouTube channel called AI in Games by a guy called Tommy Thompson. I know Layla Porter's got a good talk on GOAP and other planning systems. But for completeness sake, I want to show you the AI in IamJam. That's it. Yeah, so the AI in IamJam is really, really simple. The mice run from left to right. And they try not to fall off the cliff and commit suicide, because that would be a really terrible enemy. Our simple AI just gives the enemy like an X velocity of 4 pixels per tick in whatever direction it's facing. Now, every tick, the enemy looks ahead and sees whether it would fall down a pit. And if it's going to fall down a pit, it turns around. Now, the really interesting thing about building this AI is originally I built an AI that looked where the player was and ran towards the player. And what I found was the game was really, really, really difficult because the mice were really aggressive, and everyone would die about a third into the level because if they didn't time a jump perfectly, the mice would never kill themselves, they would never fall into holes, and they'd just get the orange. And I thought it was a really good example of where like you can build the best AI in the world, but the best AI in the world is definitely seriously unfun and would not make a good video game. So I can't really do a whole talk about building games without a live demo. So I think this might work if you scan this QR code. I didn't try it this morning, so I hope it works. It should work on your phones. There's touch input. You could even plug an Xbox pad into your phone or use a keyboard and mouse. I'm super, super proud of how this fun little game turned out, and like kind of flawed by the really great artwork. The event that it was used in was a hit. We had people trying to exploit the game. They got really addicted to it. People were like using high refresh rate laptops to go faster, and we had to fix a bunch of bugs in the rendering engine. It's really quite fun. Does it work? Yes. Perfect. Yeah, so why would I even build this? Surely this is just like a colossal waste of time, right? There's loads of game engines in the world. There's loads of game engines in JavaScript. Okay, so I think if you're looking to learn the primitives of how game engines really work, it's worthwhile building toy engines to flesh out each of these subsystems so you really understand what they do. The truth is, if you just want to make a video game, generally just pick something that's fairly well worn and used by people. You know, in reality, in the 2020s, just use Godot or Unity or Unreal or Phaser or whatever. But there's nothing more fun than working out how stuff really works. So for me, this was a little bit of a learning activity, and it was maybe the 10th, 15th game I built. So I hope you've had a little bit of fun here with me, learning about something that's not normally the regular NDC topics. And if you find the secret in the game, there is a secret where you can do like a super high jump, and you can get really good time. So I hope you've had fun. Please, please play more. Don't just do programming that's boring work stuff. Like, programming is more fun when you do it because it's cool. Have fun at the rest of the conference. Thank you so much. Oh, I also wrote a kid's book about this. I forgot, my second kid's book, I should always pimp this, is Get Coding 2. It's on Amazon. It's all about building game engines from scratch. I forgot about that, sorry. And actually, this game engine came from the final example in the book. Was that fun? Something new? Something weird? Awesome. Thank you so much.